Welcome everyone to this week's online causal inference seminar. Today we have Professor Helby Petersen from University of Copenhagen giving us a talk on what are we discovering, two perspectives on interpretable evaluation of causal discovery algorithms. The discussant today will be Vanessa Didelez from the Leibniz Institute for Prevention Research and Epidemiology. The Q&A will be handled by Sarah. Do you want to say a few words, Sarah, on the format?
Okay, so if you have questions, please use the Q&A function instead of the chat. And then we will read the questions at the end. And if there are some kind of follow-up discussion, we may also ask you to unmute yourself and you can discuss things with Anne or with Vanessa. Okay, perfect. So Anne, I'll let you start.
Without further ado, and please take it away.
I'll just share my slides. I think I'm sharing the right thing.
Yeah, you could put it in full screen.
Wonderful.
Yeah, wonderful.
All right. So thanks for this opportunity to talk a bit about a topic that I've been very interested in for a few years now. So the overall topic of today is of course causal discovery. So we're going to discuss how to evaluate different procedures that aim to try to learn something about a causal data generating mechanism by analyzing empirical data. So this is the general setup. We have some data, we have some fancy machine learning, and then we want to learn maybe a DAG, or more realistically often, we want to learn a equivalence class of DAGs. For the stuff I'll cover today, we're going to assume that there's no unobserved confounding and no unobserved selection. So we're in a simple case where everything is just a DAG. Okay, so for this task, there are a lot of different algorithms available. This is one of the classics in the field, the PC algorithm, but there's been many proposals throughout the year using different interesting ideas, different techniques to sort of go at the same problem. And I think really a defining characteristic of the causal discovery field is that it's a very productive group of especially computer scientists who are producing a lot of algorithms. And a lot of them are also have nice properties. You can prove mathematically that they're sound, they're complete, and they work in if you have infinite data. But how do they then work in the real world? That is something we know less about, or just in finite data even. If we look into the empirical sciences, I think the uptake is what we can call quite limited. This is a quick search on PubMed, which covers a lot of medical and health science publications. I've tried to limit the search to not include only strictly methods papers, but something that has at least some component of empirical data. And as you can see here, there's not a lot of publications. The peak is in 2023, where there were 12 publications using some of these methods. Yeah, and even not all of those are real empirical studies if you look into them. So how does that compare with other machine learning topics? Well, if we look at neural nets, it's a little bit of a different number. If we look back to 1990, now we have 18 publications. So causal discovery is pretty much as applied as neural networks were in the beginning of the 90s. So that's there's not a lot going on there. If we can use this graph to extrapolate, it's interesting though, because then in 35 years we'll have a lot of different publications using these algorithms in practice. But I think, as we'll also see in some of the stuff I present today, maybe there is still some work needed before we reach that goal. Other than not being used much in practice, we also have some first signs of what I will call a reproducibility crisis. There's a lot of interest in the causal discovery field for trying to understand why some of the algorithms that first seem very useful do not perform very well when you use them on new data. And especially some very interesting and very useful ideas about using continuous optimization to solve the problem have had a lot of scrutiny afterwards. And there's been a lot of literature on why that might not work as well as you would have wanted it to. So how do we move forward from there? We have a lot of procedures. We don't really know if they work in practice. And what I'll propose today is to think more about how we evaluate these methods and how we come to know what works and what doesn't work. So I will divide it into two different evaluation questions. One is, how well do causal discovery algorithms perform in an artificial controlled environment where we know the true data generating mechanism? And the other one is, how do these algorithms then provide information in real world application, and is that information useful? That's going to be the two different parts of this presentation. So starting with part one, what happens in the controlled environments in our lab setting? Well, in order to discuss that, I'll just briefly introduce how we actually do go about evaluating causal discovery algorithms. The most common strategies is to either do a simulation study where you simulate some data from a known DAG. You simulate a DAG, you draw some data from it. Maybe it's linear, maybe it's Gaussian. And then you apply your causal discovery algorithm and you compare the truth with what you estimated. A different approach that's also often combined with the first one is also to apply causal discovery to a small selection of real-world data sets. There's sort of a list of data sets that people often use, and these data sets, there is some consensus about what the true data generating mechanism is. Maybe it's been, for some of them, it's been tested experimentally. So then you compare with a true DAG from that setting. And in either case, you need some sort of metrics to do the comparison. What's very commonly used in this field is to focus on standard machine learning prediction metrics. Then that's been adapted to fit sort of the graph measurement problem. That could be adjacency or edge orientation, precision and recall, or it could be some other metrics. There's also some focus on using something that's specifically developed for graphs. That could be the structural Hamming distance. And I'm going to introduce the first two here a bit more in just a bit. And then finally, there have also been some proposals for metrics that are specifically aimed at sort of the causal elements of causal discovery. So something that tells you how much will this impact your causal inference. I'm not going to talk more about these today, but I think a lot of the methods that I discussed could also be generalized to apply to them, and also some of the problems. Okay, so the basic example, what do we want to do when we want to evaluate a causal discovery algorithms? Assume we here have a true DAG and we have an estimate of it. We want to compare them. So one way to do it is to compute the structural Hamming distance. This is a measure that counts how many different operations you need to do on the estimated graph in order to turn it into the true DAG. So in this case, I've marked that you need to add two edges in green. You need to remove one in orange, and then you need to reverse the directions of two of them. That's the yellow ones, and that gives you 5 different operations. So it's quite an easy and simple thing to do, to just count how many operations you need to do to turn one into the other. A different approach that's often also used, and that I'll discuss today, is to focus on these metrics that come from machine learning. One is precision and recall. Here I call it adjacency precision, adjacency recall, and that's because we're now comparing the graphs where I have removed all the orientations. So we're just talking about where the edges are and not which way they turn. And if we want to do that, well, then again, we need to count on our estimate. How many true positives are there? So how many edges are correctly placed? How many are false positives? How many are there that shouldn't have been there? How many are true negatives? How many shouldn't be there and are not there? And then finally, how many are false negatives? And those are the ones that should have been there but are not. So we can compute or just count those numbers and then compute these metrics. So we find an adjacency precision here of 0.86, a recall of 0.75, and that brings us to the important million-dollar question: are these big numbers or small numbers? Is this a good algorithm or a bad algorithm? And that's really the key question that I'm going to try to address in the first part of this talk. And I will be presenting some work from this paper that's an archive, where we try to sort of set a baseline for comparing these numbers too. And this baseline will be based on random guessing. So the idea is to consider random guessing as a simple common baseline for evaluating these algorithms. So in order to say if this is a big number or a small number, we'll say, well, what would we get if we just performed some random graph construction? So we just randomly drew a graph. And the motivation for doing this is that I think it makes it easier to, first of all, consider what kind of causal discovery problems are easy and which ones are hard. Maybe this one was an easy problem. Maybe it's not that difficult getting a high number, or maybe it was a hard causal discovery problem. It's difficult getting a high value, and then we should be more impressed by an algorithm that does it well. I think it also increases interpretability of the reported metrics if you compare different simulation study designs. Each simulation study has its own settings, its own sort of graph types. And by comparing them to these random guessing baselines, maybe that will help understand how we transport results from one setting into another. And then finally, there's also an element of describing how informative a given evaluation study is. Maybe in some cases, we can trivially attain high performance, and then they're not that interesting for actually understanding whether an algorithm does well or not. And I'm going to describe it sort of as a negative control concept. This is something I personally am familiar with from epidemiology, where it's an approach to sort of understand all this complex designs where you don't can't fully describe everything that's going on. So instead of describing exactly how hard the problem is, we'll just compare it to something that has no knowledge about the information, about the data generating mechanism. All right. So to give you a simple example of how you can do this using just simulation, very simple simulations, let's consider this setting. So there is one of these infamous causal discovery evaluation data sets is the SACS data set. It's a benchmark data set. It's something about protein signaling, and it has a true ground truth DAG with 11 nodes and 20 edges. It looks something like this. So that's the ground truth. We have data on it, and then we can use it to sort of see if a certain algorithm works well or not. And I will specifically focus on the no-tiers algorithm. This is a causal discovery algorithm that's been proposed in 2018, and it uses some continuous optimization things. So as I already mentioned, this was a very interesting algorithm when it was proposed, and it really has led to a lot of very fruitful research, but there has also been some scrutiny and some interest in exploring when it doesn't work well. So yeah, that's no-tiers. And in the original paper that I've cited down here, they include an application to the SACS dataset as one of their evaluation strategies. And what they found was a DAG with 16 edges, and they had an structural Hamming distance of 22 for that DAG. They don't show the DAG, so I haven't included that, but that's what they report. Oh, something from my slides went away. Oh, well, you can compare that with a negative control by simply simulating a large number of DAGs with the same number of edges as no-tiers found. I think I did it 1,000 times, and what you find is a structural Hamming distance that's of the same range as this. I think it's about 25, and you can also use those simulations to obtain a confidence interval for that number. So just by looking at the distribution, you find in these simulations, and then you actually find a 95% confidence interval that has 22 as its lower limit. So this suggests that maybe even from this simple evaluation, you would actually end up concluding that there is no significant difference from random guessing on this specific application. And that's so that can be a way to sort of understand how we should interpret this structural Hamming distance of 22. All right. So that's how we can do it if we want to use simulation for it. But if we are in this simple setting I also showed you before, where we just want to try to understand the differences in two graph skeletons, so the adjacencies without the orientations, then we can actually do it even simpler. So this is the same example as before. And instead of just considering precision or recall, we can describe the full the confusion matrix here. So this says what the truth is and what the estimate is. And I'm just adding a bit of notation. We will call the total number of estimated edges mest, the total number of true edges mtrue, and the maximum number of edges in the graph mmax. And what I want you to note here is that mmax is a mathematical property of the graph. You can just say how many edges can there be. It has this formula. D is the number of nodes. And if there exists a known ground truth, then I think it's also very reasonable to consider mtrue as a fixed unknown number. And then something that's maybe less intuitive, if you haven't worked a lot with causal discovery, is that the way most of these algorithms are being used in practice, est is also something that's not estimated. It's typically chosen implicitly using a test significance level in the constraint-based algorithms, or using a penalty for your scores. For instance, if you use a BIC score in a score-based algorithm, then there's a built-in choice of how many edges are going to turn out. It's not something we typically tune the algorithms to estimate. So at least for now, we will also consider ms fixed. Then the key observation in the article is simply that if we have random edge placement, so if we're randomly constructing a graph, well, then we actually have the number of true positives will be will follow a hypergeometric distribution with these parameters. And this is an exact distributional result that comes simply from having this continuous table structure and conditioning on these totals. You can also provide an argument that that uses sort of an ERN argument where you're sampling random edges and independently, and then you turn up at the same result. So we can actually describe what number of true positives we should get under random guessing. And that leads to a number of, I think, useful results. So first of all, that means that we can do an exact overall test of skeleton fit simply by considering the null hypothesis that a graph that we have estimated was obtained by randomly placing a number of edges. So note here that we're conditioning on the number of edges again. That's something we need for this result to work. Then we can compute a one-sided p-value for this hypothesis by simply looking at the probability for getting something that's at least as extreme, so a bigger number of true positives than what we've observed when we have x is actually hypergeometrically distributed with these parameters. Okay, so that's something we can very easily compute for a given setting. And I want you to note again that this is an exact test, so it will be conservative. And especially if the graph is small, it will be quite conservative because of the discreteness of the whole thing. But it's also a very crude null hypothesis. So I would think that we generally want to be quite far away from that hypothesis. So maybe it's not too bad to have a conservative test. I will return to an example of this a little bit later. Okay, so what else can we do? We can also compute the expectations of some of the different metrics that we get from this confusion matrix. We looked at the precision before. If we look at that, we can use the fact that we know what the expectation is of the true positives because they follow this distribution. So we have a formula for that. And then since many of these different machine learning metrics, they're actually just linear transformation of the true positives when you condition on those things, then you can compute expectations for them. And you can also draw inference by using the quantiles from this distribution. So I have a small example with precision. Precision has this formula. That's just standard definition. We can rewrite that as the number of true positives divided by the total number of estimated edges. And using that and inserting the mean up here, we get a closed formula for what the expected precision is if you're just doing random guessing. And we can also get a confidence interval for it by using the same logic because of the linearity. So that's quite neat. We can do this very easily, and we don't even have to do simulations if we're just interested in these skeleton metrics. And I think, at least when you look into what people are publishing, that's usually the first thing they look into. I've also computed the same thing for some of the other standard machine learning metrics. You can just do the same little exercise. And I think there are some interesting points here. First of all, we can note that when we have, this is the negative predictive value and specificity, they don't really have extra information to bring when you're doing random guessing. Then they're just simple sort of, they're equivalent to just reporting precision or recall because it's just 1 minus 1 or the other. So that's, maybe you don't need that many different numbers to explain what's happening if you're doing random guessing. Another thing you don't get to say very often is that there are actually free lunches here. And I think we should be very worried about that when we think about how we report causal discovery evaluations, because precision and recall, they vary independently. And that means that the F1 score, which is sort of an average over them, or harmonic? Oh, I never know. Anyway, it will be increasing in either of them. But just to show you what that looks like, here we have expected adjacency F1 score. This is the setting where we have a 5-node DAG. A 5-node DAG can have 1, 2, 3, 4, whatever, up to 10 edges. So those are the true number of edges. And then we can choose to estimate 1, 2, 3, 4, up to 10 edges. And as you can see, we can optimize this simply by putting in more edges. So given a certain level of the true number of edges, the more edges we put in, the bigger number we get out. And that should be a little bit worrying, I think, because at least we see here that there are some scenarios where F1 will not be very informative. You can get very big values by just doing random guessing. I will also return now to the example we saw just before. We wanted to know if these numbers are big, are they small? In the small 5-node DAG example. And well, let's see what we get from the negative controls. The expected precision on the random guessing is 0.8. And we get a confidence interval from 0.71 to 1. So this is actually a scenario where precision is not informative. It's very common to get values that are 1, which is the upper limit of precision. So you can't have something that performs better than random guessing with a 95% confidence interval in this setting. If we look at recall, then we get 0.7. And we get a confidence interval that does not include 1. So at least you can say that something is better on recall than random guessing. But you still get very large values just from random guessing. So is this a good causal discovery method? Not really. And you might have guessed at this point that it was, in fact, just a random draw. I did not have any information about the DAG. And I actually chose this specific example because it corresponds to how sort of the median graph differs from a true graph. So this is a standard scenario for this setting. Okay. So I think this shows that maybe we need to consider what we compare with in order to understand these different metrics. One thing you might ask is it reasonable to really condition on this MS value, the number of estimated edges? And I want to acknowledge that maybe it's not always reasonable. If you're actually tuning your algorithm to data to get the right level of sparsity, density, whatever you want to call it, the right number of edges, then it's not something we condition on. It should be included sort of in the evaluation. The distributional results I showed you here about the adjacency true positives, they don't hold anymore. If you're in this case, if you've tuned it, I think you can still use some of the simulation-based ideas. A simple approach is just to draw from the appropriate distribution of these estimated edges. So if you repeat your algorithm a lot of times, then count how many edges does it put in, and then draw random graphs from that with the same number of edges from that distribution. I think that strategy might favor algorithms, the algorithm being evaluated, because it's tuned for this kind of setting. But I also want to reiterate a point I made just before. When we have such a crude null hypothesis and we have a conservative test, do we really care if we sort of favor a little bit the algorithm that we're trying to evaluate? Because we're not really hoping for something that's borderline significant here. We would like to do markedly better than random guessing. Otherwise, it feels like it's a waste of time applying these methods. I write a little bit more about this in the article and about how you might do it in practice. So there's an example of that. Okay, so that's more or less what I have to say about the first part, about what we do in the lab. But I will return to some of the points and how they can also be used in trying to understand what happens in the real world. Because in the second part, I will discuss this case study that we did with my collaborators, Klaus Ekström and Peter Sperdes and Merete Osler, where we tried to use causal discovery in practice in a cohort study, a life course epidemiological cohort study, where we tried to understand why some people got depressed and why some people had heart disease. And we compared the causal discovery output with a traditionally constructed model, which was some experts trying to make a DAG. So the idea of this paper was to sort of compare a man versus machine, who can get out the most correct model in some sense. So just to show you how the data structure is here, we have different periods of time where we measure different things. Across the lifespan, we have some information from when the men were born, childhood, youth, adulthood, and early old age. And then what we want to do is construct a graph for this. So we want to add some edges at reasonable places to understand how the causal flow is. Okay, so the case study design, as I said, we consider the specific case, and then we do a theory-based model construction where we have epidemiologists, who we will refer to as the experts, construct DAGs. They do not look at the data, and they both do individual models, and then they also construct a joint consensus model from that. We also have a data-driven model construction method where we apply a causal discovery algorithm to a data set based on the metropolitan cohort data set. And then we try to compare the two models. And our general way of doing that is to assume that the experts are mostly correct, but possibly incomplete. And that the data-driven model may or may not be correct, but maybe it's a little bit more complete. Maybe it has additional information that we overlooked. So just a few details about how we did the theory-based model construction. So we had experts in heart disease and psychiatry, epidemiology. They were giving a list of the variables without any data, but they were given the temporal information. They were also given a little bit of information about the intended study population. So when were they born, and where. And then they were also given written instructions for doing these DAG constructions. We asked them to annotate each edge with a label of confidence, either moderate or high. And then we had both individual models and a joint model, as he just said. And just to give you an example of what that looks like, this is one of the experts' graphs. Their individual model, they had a template and then they could draw in their edges. And that's a very time-consuming procedure. I'm sure a lot of people here know. Okay, then what did we do for the data-driven model construction? Well, we used the temporal PC algorithm, which is a temporal modification of the standard PC algorithms that sort of makes use of this temporal data structure where you have variables assigned to different periods, so you know there can't be any causal links against the direction of time. There are different ways to use that information, and this specific implementation is available in R in the Causal Disco package, and also in the TPC package in R. And there's also something in Tetra, which I think might be a little bit different, but I think it's the same overall ideas. So we use this procedure, and we have to choose the test significance level because it's a constraint-based causal discovery algorithm. So what it does is to do a lot of conditional dependence tests. And the way we did that was to actually tune the algorithm to have the same number of edges as what was proposed by the expert consensus model. So they had a number of edges, and we just try to find something that was the same. So here's just a little bit of code example to show you that this is something that's quite easy to use and also easy to inspect. So the final command here produces plots that look like what I have on the next slide. Okay, so this is the result from the expert model. And what you might note here is that some of the edges are blue. Those are their high confidence edges. So those are the edges they have the most trust in. And here is the estimate from the causal discovery procedure. And we can compare them in many different ways, look a little bit back and forth, and they're not equal, but they're not that different. So we might want to summarize that information. One thing we can do is to look at this adjacency confusion matrix, where we look at what the experts put in and what the causal discovery algorithm put in. And I just want to note, before we look a lot into those numbers, that this is actually most of the information there is about comparing at least edgewise, compare these graphs edge by edge, because they do not disagree on orientation. There's only one edge where the causal discovery algorithm does not orient it, but the experts do orient it. I think it's this one from weight to length. That's sort of the only difference in orientations. So it makes sense to mostly talk about these adjacencies. So we see that these two, the experts, they agree with the causal discovery about 10 edges. Then there are 20 edges proposed by the experts who are not in the causal discovery output. And there are 20 edges proposed by causal discovery that are not in the expert output. And the symmetry here is by construction, because we tuned the causal discovery algorithm to have the same number of edges as the experts had in their graph. If we look specifically at these high confidence edges, then 6 out of the 7 are found again by the causal discovery procedure. So that's the blue ones. And I think the one that it misses is, no, that's not it. Well, it misses only one. Yeah. So you can look at this and say, well, that's a lot of correct adjacencies and non-adjacencies. In some sense, these 10 are correct, and these 181 are also correct. Oh, that's the wrong number. But how many of those should we have expected to be true if we actually just did random guessing? And it's actually that question that motivated a lot of this negative control work. What would we have expected to find if we were just randomly guessing here? So let's have a look at it. Well, the observed precision and recall we find here, and those are equal due to the symmetry in the true number of edges and the estimated number of edges, is 1/3. That's not a very big number, usually, I would think, for precision, but let's see. We can also compute the structural Hamming distance. That's quite easy, because we only have one edge sort of orientation that differs, and then we have 20 that are there but shouldn't be. And 20 the other way around. So that's 41 operations. If you want to know if these numbers are high or low, we can use the methods I just showed you before. We can find the expected precision or recall under random guessing. That would be 0.13. We have a confidence interval for it, and we also have a test of overall skeleton fit where we find a quite small p-value. So I would say this is an unlikely estimate to find if we are just placing edges at random. So at least that's nice for the causal discovery procedure here. It doesn't look like it's just placing edges at random. We can also, using simulation, find out what the expected structural Hamming distance would have been under random guessing, and then it would have been about 13 edges extra. And we have a confidence interval for that as well. So that can help us understand what these numbers mean and how we should interpret them. Then that's really not what we were talking about in this part of the presentation. I wanted to know if the causal discovery insights are actually useful. So in order to discuss that, I think the main focus should be on the 20 edges that the causal discovery procedure proposes that the experts do not, and what we can say about those. And we tried to classify those post hoc, so after the fact, after we've seen them, into 3 different categories by revisiting the literature on the different proposed causal links. And we found that 3 of them had low plausibility, which meant that we could not find anything that suggested they should be there, and they did not go with existing theory. 6 of them were moderately plausible, so we could find some suggestions that they might be there and some convincing arguments. And actually 11 of them had high plausibility. So we could find several different sources that found them plausible, and they fitted well with existing theory. So it seems like what we discover here might actually have some use and be something that the experts overlooked at first. I have 2 extra small examples of how you can also try to look closer into a model to understand what comes out of using causal discovery versus the expert model. So how do they differ? One is a it's an example where we focus on socioeconomic variables. So we might have a specific type of variables that we're interested in, and then we can see how much do the models differ for that. And in this case, it's social variables, so something that's associated with socioeconomy. It's stuff like low paternal social class, marital status of the mother, employment status, retirement, cohabitation, education. Then I mark all the edges going in and out of those. And I can count here in the expert model how many social edges are there. There are 10. And how many non-social edges are there? There are 20. All right, let's do the same for the causal discovery procedure. We've marked them, and we've marked all the edges going in and out of social variables. And you can see that there are a lot more of them in the causal discovery procedure. We find actually 20 social edges. 15 of them are new, so they were not proposed by the experts, and only 2 of those are implausible. So this is an example of how we can try to understand what extra information the causal discovery procedure brings to the table. And I think in this case, it suggests that our experts were not very focused on socioeconomy. They were maybe more focused on different kinds of risk factors. So at least that's a way to describe that. A different example of what you can do with this is to consider sort of the structure of the graph. Here I'm focusing on lag. So that's how many periods an edge skips. So here would be an edge with lag 0, and one with lag 1, one with lag 2, and 3 would be skipping more, and so on. So we can count in each of the edges, each of the graphs, how many different edges have different lags. Here are the experts, here are the causal discovery results. And one thing that pops out for me here is that the experts sure seem to like lag 1. There's a lot of those, and a lot more than there are in the causal discovery procedure. The causal discovery procedure seems quite focused on lag 0, but I found this table to be a little bit difficult to interpret. So once again, we might use these negative controls to sort of understand how much of this information is just embedded in the structure we have with these different tiers, where they can be different lags of different numbers of lags, and how much is specific to this application. So we can compute these are averages from negative controls. We can also compute p-values, where we compare these numbers to that number and this number to that number. Those are the ones in parentheses. And in blue, I've marked the ones that are significant at a, say, 5% level. So what we can actually conclude from this is that the experts have a markedly different lag structure than the negative control. But the causal discovery algorithm actually does not. It has more. It has significantly too many, like 0 edges, but the rest of it is not different from negative control. So it seems like our experts, they have a distinct preference for lags of size 20 and too few of size 2 and 3. And maybe that can give us some insights into what kind of sort of preconceptions are included in how the experts operate. Yeah. So what would be the conclusion from this application and the case study? I think it is that causal discovery can be a tool that can help focus attention on something that's maybe overlooked in an expert DAG, and it can be a good complement to using the traditional procedures. So we should have man and machine going hand in hand and sharing their perspectives. Okay, I think we're reaching the overall conclusions of this talk, and they're going to be a little bit in different directions. First of all, I think the first conclusion is that we need to be a little bit more ambitious when we evaluate causal discovery procedures in the lab, so in the simulation controlled environments. We need to think about how we design our simulation studies, because the results are incredibly sensitive to some of the choices we make, especially what I've shown here is how sparse the true data generating mechanism is, so how many edges are in that, and also how sparse the estimated graph is. We can really get any specific number out of a lot of the metrics if we just change those factors. So we need to think about that. I think we should also be cautious about how we're comparing different algorithms that's been evaluated in their own separate simulation studies, because we're really often comparing apples and oranges. If the simulation studies did not have the same estimated and true sparsities, then the comparison is really not that meaningful, because some of them are hard questions, causal discovery questions, and some of them are easy ones. So it's difficult to compare them. I think I also showed that some of the custom-made evaluations you might use for a specific scenario, so for instance, the lag comparison, can also be a little bit difficult to interpret alone. So maybe we can also think about how to help that kind of evaluation. And I think these negative controls can help a lot. They don't say everything there is to say, because it is a very crude null hypothesis, but maybe we need to just first check, are we even doing better than random guessing, and how much so? And they're very easy to do, and especially if you're in this skeleton metric situation, you can just use the closed formula that I provide. Well, what about the real world? I think here we need to be less ambitious. When we're considering how useful these algorithms are, I think we should think about where the relevant appropriate baseline is. What is treatment as usual? It's often not oracle information. We never have that in practice. So I don't think it's a fair or meaningful comparison to talk about the true data generating mechanism. Rather, we should see, what are people doing now? Can we do better than that, or just equally well? Yeah, I think the Methodological case study provides an example where we actually find some additional information by doing causal discovery that could help understand more about that specific case. And I also think using causal discovery actually provides some insights into the implicit preconceptions of these experts. They focus a lot on one-period lags, on unsocial factors. Maybe this will broaden their view, or at least they will know what sort of implicit assumptions go into how they work with this. Finally, I want to finish on a question that I'm often asked, and I thought I would use this opportunity to try to answer it. Are these causal discovery algorithms actually mature enough to be used in the wild? Should we do it at all? We don't know if they work really. And my answer to this is that I don't think they'll ever be if we don't start using them in the wild. We really need the insights that come from applying these things to real world data to understand what happens outside of the lab, and also the limitations. I think, for instance, the no-tears algorithm, seeing that it does poorly on a real data set should have started some alarm clocks, and then we could have understood, why is that happening? Why doesn't it transport well? I think the algorithms also have a lot to offer, and and constructing DAGs is difficult. So there is a lot to gain here. And I just want to also bring a few resources on the topic of actually trying to use these things in practice, focused on health sciences, because that's where I've mostly looked at it. Vanessa Didelez, who will be doing the discussion, has written a very nice resource on all the different things that are difficult when you want to do this in practice. And we also have a comment on that. And then a new article that tries to sort of bridge this with system dynamics things and try to understand how you might use both in order to get a more robust result. And I think I will end on that and an advertisement. We're looking for PhD students. So if you're interested in something like that, maybe on causal discovery, then please check out this link. Thank you.
Thank you very much, Anne, for your very interesting talk. Sarah, do you want to do the questions now, or maybe after Vanessa's discussion?
Maybe you can do one very quick one, which I think is like one or two which are clarifying, and then the others are pretty long, so maybe we can do them a bit later. So
Okay,
I wanted to ask you
let's
first
do
a
those.
clarifying question from Jakob Zeitler. So you can see the questions in the Q&A. Jakob is asking, did I understand correctly? The algorithm was told how many edges there would be. This is in the expert part. So therefore, we got the symmetry in the comparison matrix with the experts.
That is exactly correct. Yeah, so we told the algorithm that it was going to have 30 edges, and then we wanted to find something that had the same level of information, just to do a clean comparison.
Okay, there was another question, which I hope is relatively quick. Does this work for any type of DAG, or not? It's not just DAG, I think it's mixed graphs, like MP-DAG, CP-DAG, MAG, PAG, etc.
Well, that depends what you want to know. So I don't think that's a quick question.
Okay.
Maybe we need to return to that one.
So it doesn't work directly. It may need some more work.
Well, it depends on what you want to do. You can always do skeleton comparisons in any of them. If you want to use some of the orientation information. I don't think it's often that informative what you get out of doing the simulations. I've tried on V structures, for instance, and it doesn't, nobody really finds those apparently. Yeah.
Okay, so then
the short answer.
I think thanks for the answer. In the interest of time, I think maybe it's good that Vanessa does this. Starts.
Yeah, Vanessa, whenever you're ready.
I think so. And if you want to also quickly check the questions as well, you can check them.
Does this look okay?
Yeah, I can see it.
Okay, and you can hear me. Okay, great. Thank you very much for the talk, and thanks for the opportunity to discuss this talk. Anna was showing us some skeptical and reproducibility crisis sort of slides at the start, and I want to, I can't see everything on my own slides now. Wait. I want to echo some of this, and I was reminded that there was an interesting talk by Dominik Janzig last year at the UAI. He said that all DAGs are wrong, but some are useful. Anna showed us some examples of how they can be useful, but he also reflected a bit disillusioned on his own experience, saying that causal discovery, not only that the results are often wrong, even worse, we rarely know whether they are wrong. So this is maybe where Anna's suggestions help. And even worse, we rarely understand what wrong means. I think maybe there we still need to have more thought into that still. Let me remind you of what is hard about validation and causal inference is we can't just use the same data or similar data, because the ultimate validation is really about, or causal inference is about making claims about other situations. So the changes in situations. The ultimate validation is carry out the relevant interventions and check if your causal claims hold up. And there are only few, maybe in genetics, I think there might be more examples, but there are only few real examples where this can be done with causal discovery. I recommend this nice paper. So in many contexts, this is not possible. It may not even be meaningful, but then the question could also be, if it's not meaningful, why do we construct a causal DAG? In any case, we should choose the evaluation that matches the purpose of the analysis. In a causal DAG, if we want to validate this, we must intervene on very many nodes if we want to check the whole DAG. So it's not just that simple. So what we use is simulations, and that's what Anna showed us in simulations. And what Anna proposes is what is the baseline. Random guessing is probably the lowest bar, but this is easy to do. And I had the same question, like one of the questions in the audience, why don't we always just do this? It seems obvious, it's easy to include in simulations. And you might also choose your own definition of what you think random guessing is. And it's also urgently needed because there's a surge of new, not always very transparent methods around that maybe need to be checked against this very low bar. Anna proposed what she wanted was some sort of test of better than random guessing. I'm not so sure that I understand the use of this test, because when we are doing a simulation, where we need to know the truth for the test, when we are not doing a simulation, we can repeat many times anyway. We don't need a statistical test. And in other situations, we don't know the truth. And I also think I still need to think a bit more about whether there are cases where we might not want to use this Erdős-Renyi type random guess, but something else. Yes, and of course, as I already mentioned, and as Anne mentioned, the real-world ground truth is very rarely available. So that's also, we must be very lucky to have this for validation and causal inference. Let's think a little bit about random guessing. We know from classification tasks, when we draw ROC curves, what the random classifier does. And this is also what you can do in undirected graphs. So when you evaluate skeletons, and this is what is being done, and with many repetitions, you would hope that you don't have so much randomness, that you can draw the expectations. But Anna wanted the distribution, and she also calculates precisions and recall graphs, where also we know, at least in expectation, what the random guessing would give us. But this doesn't help with other measures. And this is where I see the value on DAGs, other measures on DAGs, like the structural Hamming distance, for example. So looking at random guesses to evaluate other typical measures that are more geared towards the causal elements of the DAGs, and not just towards the skeleton. That's where I find this very interesting. Anna described this as a negative control concept. Here I disagree, because unless it's a very different usage of the word, negative controls I know as being about detecting or quantifying bias. I'm not sure whether this is about quantifying bias. It's about comparing with a null hypothesis of, drawing some DAG that doesn't use information in the data. And there are two different things, I think. And oops, I'm sorry, I want to go back. No. When a method does badly, we don't know why it does badly. It's not necessarily bias, I think. So it could be that the assumptions are violated, or which maybe in a way is bias, but we don't really know why it does badly. There's another way of looking at random guessing, and I came across this paper in preparing for today, also by Dominik Janzig, where they want to evaluate a user-given DAG against the data, needing a random baseline, and they construct random draws by node permutations. They do a bit more. It's not really the same sort of question as Anna's, but they also show that they can use this to evaluate some causal discovery algorithms. And they, like Anne, they looked at the Sachs data and the no-tiers algorithm and came to not very favorable conclusions. They say, in our experiments show that better than random is a surprisingly high bar, and both domain experts and causal discovery algorithms fail to meet it in many settings. One word of caution is that with all this evaluation, even against some random guessing, this is still some sort of statistical model fitting, or looking at, does it statistically differ from random guessing? But it's not about the causal nature, which really needs evaluation under some changes, something like interventions, some changing circumstances, distributional shifts, natural experiments, etc. About the expert side of things that Anne mentioned, there's this critical article which maybe was in response to Anne's work, and they are a bit more extreme because they say, can we replace expert knowledge by algorithms? And they are very, very critical. But as we have seen, there's also good reason to doubt expert knowledge. There are lots of problems with how experts construct their knowledge. I think they find it difficult to think about edges because they are direct causal effects relative to the other nodes. And that's always a difficult operation for experts to do. They need a lot of eliciting here. And the other problem is that we need to think about the nodes that are not there and the edges that are not there, which is also difficult usually in communicating with experts. So I think the way forward, like Anne said, is combining experts and data to construct DAGs. There are many proposals already in the literature, but again, they are not very widely used, perhaps because often it's not the right form in which expert knowledge is available. It comes in very different forms. And this is the important challenge for the future, to have good ways of combining different types with different certainty and uncertainty about the edges, partial knowledge of that experts have on direct or indirect relationships, etc., and to combine all of this with the construction of DAGs. I finish here, and it was a pleasure to discuss this and a lot of fun. Thank you.
Thank you, Vanessa, for the nice discussion. Do you want to respond to any points and from Vanessa's discussion?
I think Vanessa makes a lot of very important and good points. I think one thing is about terminology and these negative controls. Maybe we should call them random controls or something like that. I think the motivation for calling them that is because they're supposed to happen in a setting where there should be no signal from what we're trying to find. And I think that's sort of the metaphor that goes back into how we also use in the different fields. Having something where there really shouldn't be anything going on, but it's not bias, and I think that's a very important point, that it's different from that, and it's cruder. Yeah.
Okay. Sarah, do you want to go over some more questions, perhaps? We have 2 minutes.
Yeah, my connection is a bit unstable, but I hope it will work. So I wanted to start with some questions from Karen Marsban. So the first question was, in some fields, for example, meteorology, in addition to comparing the contingency table with a random contingency table, one also...
Okay, it looks like we're losing Sarah. Okay,
I guess I can continue.
And maybe we can wrap it up from there. So this is a question from Karen Marsban. So in some fields, for example, meteorology, in addition to comparing the contingency table with a random contingency table, one can also compare it with what it would be if all predictions were for one class or the other class. Might it be useful to also study those limits in this causal discovery context? I think it's basically like a full graph.
Yeah, so that would be a full graph or a completely empty graph. And I think we can report that, and it's easy to see sort of what would happen for the different metrics in these settings, but I'm not sure that would bring extra information to evaluating a specific procedure. But yeah, I showed a graph where we can give a trivially high F1 score if we just put in all the edges in a random guess.
Okay. This is another question. We will do this last one. It's fairly long. I'm going to read it. If a TPC discovered edge was deemed highly plausible due to multiple different sources of literature supporting and fit well in existing theory, why were they missed by theory-based model initially? A better way to formulate the question is, how exactly would the moderately plausible edge and highly plausible edge differentiated? Was there an objective criterion or only a subjective criterion?
Yeah, so I think why were they different? And that's what Vanessa says, right? This is not an exact science. It's difficult to do it. There are many things about how you understand what it means to construct these graphs. We have tried to sort of make it more formalized procedure by having the experts have instructions for it, but it's still not very easy to see if they come to think of everything that should be there. So I think that's why they might differ. And the way we categorize them, we had some specific rules for when they should be moderate and when they should be high. As far as I remember, it was something about having both empirical and theoretical evidence, at least for the high one, and then for the moderate, it had to have one or the other. But I am not completely sure of the definition. It's in the paper.
Okay, thank you very much. I think this is a good time to make a stop. There are more questions. I'll send it to you and after the seminar.
Thank you.
So let's wrap up. Thank you again, and Vanessa for the very interesting talk and discussion. So next week we'll have Michelle Coasar from Princeton University giving a talk on evaluating counterfactual policies using instruments. And we have a discussant, Edward let's say, I'm sorry about my pronunciation, from Yale University. I'll see you next week. Aditya, you may need to stop the recording, actually. I don't know how to stop recording. I think I sent a request.